Hello, today we will explain our result for group assignment. First, we will introduce ourselves. My name is Ahmad Bakhtiar and my contribution is to handle Excel and demonstrating the method to obtain relative permeability.
Hello, my name is Anik Imran and my contribution is in charge of video editing and slide presentation.
Hi, my name is Nur Fatin Raifah Huldani binti Abdul Syukur. I'm in charge in slide presentation and organize Excel sheet.
Hello, my name is Sharul Zamri and my contribution is in charge in slide design, slide presentation and conclusion.
Capillary pressure is the pressure difference between two immiscible fluids in the pores of a porous material, typically in the context of oil and water or gas and water in the reservoir rock. Capillary pressure can be measured in three ways, which is first, mercury injection capillary pressure, second, porous bed method, and third, centrifuge method.
Relative permeability is a measure of the ability of one fluid to flow in the presence of another immiscible fluid within a porous medium. It is dimensionless ratio with range from 0 to 1. How we measure relative permeability is by, firstly, steady state method, second, centrifuge method, and lastly, capillary pressure and imbibition method.
There are several methods in finding the relative permeability. So for the first one, we use per cell approach, which we calculate the 1/PC squared for each data and tabulate in the table. And then area of each interval was computed from the graph of 1/PC squared versus saturation water. And then we will get the area of each interval and the area of absolute, which is the total sum of interval area. And for the cumulative area, for the wetting phase, is the sum of each interval area, and for the cumulative area for non-wetting phase is the difference between area absolute and cumulative area for wetting phase. And then the relative permeability of wetting and non-wetting phase was obtained by dividing the cumulative area with the area absolute. And then the obtained relative permeability is plotted into the graph where relative permeability is y-axis and water saturation is x-axis. For the second one, we use burden approach, which is quite similar to the per cell approach, and the only difference is that burden approach uses lambda, which is the tortuosity ratio for each wetting and non-wetting phase. And to finding this, lambda for wetting phase is equal to water saturation minus irreducible water over with 1 minus irreducible water. And for the lambda for non-wetting phase is equal to 1 minus water saturation minus with equilibrium saturation of the non-wetting phase, which is equal to 0, over with 1 minus irreducible water minus 0. And then the relative permeability for wetting and non-wetting phase can be calculated from the lambda square times with division of area cumulative and area absolute. The obtained relative permeability is then plotted into a graph where relative permeability is y-axis and water saturation is x-axis.
For a relative permeability method, we will use equation 8, where SW star is computed to obtain relative permeability of wetting and non-wetting phase. To obtain it, SW star is computed by using each water saturation minus irreducible water saturation over 1 minus irreducible water saturation. Obtained SW star is then substituted into relative permeability equation for wetting phase followed by non-wetting phase. The obtained relative permeability is plotted into a graph where relative permeability is y-axis and water saturation is x-axis.
For method 4, we use Brooke-Corey relative permeability method. First, we compute the normalized wetting phase saturation for each water saturation. Second, we convert the capillary equation to its linear form by taking natural logarithm of both sides. Then we calculated the ln PC and ln normalized SW by using each capillary pressure and normalized SW respectively. Next, we plot graph ln PC versus ln normalized SW. From the graph, we can get the slope is equal to -1 over lambda and y-intercept is PE, which is entry pressure. Fifth, obtain normalized SW and lambda is substituted into relative permeability equation. Then we plot graph PC against SW to compare PC calculated and PC experiment. The graph shows our linear function data is closely accurate with PC experiment. Last, the obtained relative permeability is plotted into graph where relative permeability is y-axis and SW is x-axis. Last method we use is Purcell relative permeability method. Basically, the steps are just same with previous book's correlative method, but for the Purcell relative method, we use different equation for relative permeability weighting phase, which is KRW is equal to normalized SW power of 2 plus lambda over lambda, while for relative permeability non-weighting phase equation is KRNW is equal to 1 minus KRW. For graph PC against SW, also we can conclude that data for PC calculated is closely fit with the data for PC experimental. Lastly, we got the permeability curve by plot graph where relative permeability is at y-axis and water saturation is at x-axis. For the conclusion of this project, as we can see from this graph, Purcell approach and Purcell relative permeability methods are not accurate to predict relative permeability for non-weighting phase because data point is not fit with experimental points. And the most accurate data points for relative permeability weighting phase is Brooke-Corey relative permeability method, while for relative permeability non-weighting phase, the most accurate data point is Corey relative method.